Hi guys, welcome to the live session for Computer Graphics CS603B and IT 603B for Computer Science and Engineering and Information Technology students. Before starting the discussion, I would like to say one thing that don't forget to share your name and university roll number into the chat box so that I came to know how many of you are attending this live session and whom of you are attending. Since the previous live session, we have been discussing about transformation in two dimensions. During the previous day, we have discussed about uh, homogeneous coordinates, what they actually are, how to apply them in computer graphics to get a generalized form for different transformation matrices. Then we have discussed about translation. Today we are going to discuss about rotation at first. So when I say rotation, the first thing which came to my mind is that 2D rotation is a process of rotating an object with respect to one of the primary axes by an angle in two-dimensional plane. So to get the idea in a more clear way, just look at this diagram. Say in your two-dimensional plane xy, you have a point object O whose coordinate is x old, y old, x old and y old, and you have to rotate this point object by an angle of theta in anti-clockwise direction. Now, before diving deeper into the mathematical equations, first try to observe the things, what's going on here. Your point object, you can see in the diagram that it is already making an angle phi with its primary x-axis. Now you are told to rotate this point object by an angle of theta in the anticlockwise direction, and after rotation you will arrive at a new location O dash for the point, which you can observe here. And after rotation, the new location, that means the point O dash in this case, has a new coordinate x new and y new. So the new coordinate is x new and y new after rotation. So just have a look at the statement. Initial coordinate of the object is O, x old, y old, as we have discussed earlier. Initial angle of the object O with respect to origin, or more precisely with x-axis, is phi. Then you are given a rotation angle theta. Now you have done the rotation, and after rotation you arrive at a new coordinate O dash, and its coordinate value is x new, y new, as we have discussed. Now I will like to ask you one question. Observe this diagram. After rotation, what angle this new point O dash is making with x-axis? Write down the answer into the chat box. I repeat the question once again. After rotation, you get a point O dash. Now try to figure out what angle this O dash point is making with x-axis. Write down the answer into the chat box. Hope until now you have some idea into your minds. Uh, Now let me try to figure out how we can derive the mathematical equation for this to the point xo from origin is r. Now from mathematical concept you can say that you can define this xo and yo in terms of r and phi in parametric form. If you do this, then xo becomes equal to r cos phi and y old becomes equal to r sin phi, right? Then you did the rotation by an angle of theta and you arrive at a new location xn yn. Uh, Before some time, I have asked you one question. What angle this point xn yn will make with x-axis? The answer is the angle will be phi plus theta. You can observe it here. Xn and yn is making an angle phi plus theta with x-axis. So now try to express xn and yn in terms of r and the angle it is making with x-axis. And if you express it in this way, then xn will become r cos phi plus theta and yn will become r sin phi plus theta. Hope this makes sense to you. Now express this cos phi plus theta and sin phi plus theta in explicit way. If you break down uh, r cos phi plus theta, then xn becomes r cos phi multiplied with, can you say it out, cos theta minus r sin phi multiplied with sin theta. Similarly, if you break down yn, then yn becomes r sin phi multiplied with cos theta plus r cos phi multiplied with sin theta. Now observe everything. If you observe carefully, you can find that in these equations you can replace cos phi and sin phi with xo and yo. How? R cos phi is xo and r sin phi is yo. Now if you replace r cos phi and r sin phi in these two equations, you get something like this. X nu becomes uh, X sold multiplied with cos theta, you have replaced r cos phi with x sold, and minus y old sin theta, you have replaced r sin phi with y o. At yn now becomes y old cos theta. You have replaced r sin phi with y old plus x old multiplied with sin theta. So you have replaced r cos phi with x old here. Now rearrange these two equations, or more precisely, bring x old sin theta before y old cos theta to align x olds and y olds in both the equations. So xn equals to x old cos theta minus y old sin theta, and after rearrangement, y new yn equals to x old sin theta plus y old cos theta. Now try to express these two equations as a single equation in matrix form. Here is it. Now your x and y and vector equals to cos theta minus sin theta, cos theta whole, that means the matrix multiplied with x old y old vector. If you do the matrix multiplication here, you will arrive at this equations. Cos theta multiplied with x old minus y old multiplied with sin theta. That is our x new, xn, and sin theta multiplied with x old plus y old multiplied with cos theta. That is the value of y new. Until now, you can see that we have at least had some idea about rotation matrix. Now, in this system, if you supply the value of theta and your starting coordinates, then you can arrive at the final destination. Now, this thing is not expressed in homogeneous term. So, to convert this into homogeneous format, just introduce the homogeneous one into the equation, and your equation will become something like this. Xn yn 1 vector equals to cos theta minus sin theta 0, sin theta cos theta 0, and at the third row you have 0 0 1 multiplied with x y and 1. Now if you solve this multiplication here, you will again arrive at this two equations. How? Just have a look. Xn equals to cos theta multiplied with x old minus y old multiplied with sin theta and 0 multiplied with 1. So xn equals to x old cos theta minus y old sin theta. Then let me move to the next row. Yn equals to sin theta multiplied with x old plus cos theta multiplied with y old plus 0 multiplied with 1. So yn equals to x old sin theta plus y old cos theta. And the last row, 1 equals to x old multiplied with 0 plus y old multiplied with 0 and 1 multiplied with 1. So 1 becomes 1. So you can see this is your generalized rotation matrix which you have been able to derive by following the discussion. One thing which I must mention here is that always keep a notebook with you when you are watching this video lectures. Take notes whenever you think necessary and write down the points which you think fuzzy to yourself, so that later on you can give extra emphasis on those points. So this was all about rotation, you can see here that as we have discussed, x new, capital X new equals to capital X old multiplied with x. The small x is basically the distance to the point in question from the origin, which was r. Now, in this reading material, r is being expressed as small x. Now, this is your rotation matrix without homogeneous coordinate system being involved, and this is your rotation matrix as we have derived using homogeneous matrix. Now, let's try to apply the understanding what we have been able to learn from the discussion to some real world problems. Just look at problem number 1. Given a line segment with starting point as 0, 0 and ending point at 4, 4, apply 30-degree rotation anti-clockwise direction on the line segment and find out the new coordinates of the line. Uh, I will pause here for a moment. Think yourselves. You don't have to write anything into the chat box as of now. Think yourselves how you can come up with a solution for the problem. And in the meantime, I will copy the problem so that we can have this in our whiteboard. Let me take a new page and paste the problem here. Yes, I hope that the problem is visible to everyone. And in the meantime, you must have come up with some procedures by following which you can solve this problem. Uh, so just once again, look into the problem. Before solving the problem, let me draw our x and y axis. This is our x-axis and this is our y-axis. And the problem goes like, given a line segment with starting point 0, 0 and ending point at 4, 4. That means you are given a line segment, and a line can be represented by its two endpoints. And the endpoints of the line goes like, the start point is 0, 0 and the end point of the line is 4, 4. So the line is something like this. Here is your starting point 0, 0 and here is your end point 4, 4. So next we are being told that apply 30-degree rotation towards the anti-clockwise direction on the line segment. That means here is your line at present. You need to apply a 30-degree rotation in the anti-clockwise direction. So visually you can say that after applying the rotation, you will arrive something like here, right? Now, what is the problem? What answer it is asking for? It is asking for to find out the new coordinates of the line. So let me start solving the problem. We are told that the angle of rotation is 30 degrees. So our rotation matrix will look something like TR equals to, if you can recall, the rotation matrix in generalized form was cos theta. That means in this particular problem, theta is 30 degrees. Then you have minus sine theta. That means minus sine 30 degrees. Then 0. Then you had at the next row sine theta. That means sine 30 degrees here. Then cos theta, cos 30 degrees, 0. And at the last row, we had 0, 0, and 1. So for this particular problem, this is going to be our rotation matrix. Now, how you should proceed? You are given 2 points. So first, for the starting point. So if you can recall our prior discussion, you can say that for the starting point, x old is 0, y old is 0. So now the question is, after rotation, what is going to be our new starting point? That means yn, yn, x and yn are going to be what? So try to figure out how you will put all the things into the formula. Just I pause for certain seconds, find out if you can do this your own self. You don't have to write anything into the chat box. Just in your copy, what I hope is with you, write down the formulation. Hope you have some ideas about the solution. It will be something like xn yn equals to 1. Then you will place your rotation matrix here. That means this thing. Here you should replace this with this multiplied with x old, y old, 1. Now, if you complete this multiplication, at the end you will get the new coordinate value for x and yn after rotation. So try to solve the problem as both the points are actually 0. You can say that after doing the multiplication, you will get xn equals to 0, yn equals to 0. So is the problem complete here? No. You have done the rotation until now only for the starting point, right? So you have to follow the same procedure for the endpoint also. So for the endpoint, will there be any change in the rotation matrix? No. Eventually, you are told to rotate both the start and end point by an angle of 30 degrees. So you don't need to change anything into the transformation matrix. Rather, just your x old and y old gets changed. X old is now 4 and y old is now 4. Now, to find the x new and y new for the end point, you have to multiply x old, y old, and one vector with the transformation or rotation matrix. Old, y old, 1. Here is it. If you complete the multiplication, you will arrive at um, the new location for the endpoint. So solve this yourself and try to find out the coordinates for the endpoint after rotation. Now let me look into the second problem, and the second problem goes like: you are given a triangle with coordinates 0, 0, 1, 0, and 1, 1. Rotate the triangle by 90 degrees anti-clockwise direction in the anti-clockwise direction and find out the new coordinates. So into the second problem, rather than a line, we are given a triangle, which is a polygon. In simplest form of a polygon, we can think of a triangle. A triangle, and the coordinates for all the vertices are respectively 0, 0, 1, 0, and 1, 1. Rotate the triangle by 90 degrees in anti-clockwise direction. So how you will solve this? Just think yourself for a while, and in the meantime, I will copy the problem to have it into our uh, board. I paste it here. Now you can have a look into the problem once again, and the problem goes like: given a triangle, so you have a triangle in a two-dimensional space. Draw the two-dimensional space. At first, x, y axes have been defined. Then you have a triangle, and the first vertex of the triangle is located at 0, 0. So this is, say, your starting point for the triangle A. Then you have a second point located at 1, 0, somewhere here. B, and the coordinate for B is 1, 0 as per the problem statement, and the coordinate for the starting point is 0, 0, is located at the origin, and the last vertex, third vertex, is located at 1, 1. That means, if I'm not wrong, 1 then 1, it is somewhere here. Say this is C, and the coordinate for the C is 1 and 1 as per the problem statement. And here is your, sorry, I must draw this with another color so this gets visible. Yes. ABC triangle. Now it's done. Okay. Now you can see that you have the triangle as per the problem statement. You have the corners located at 0, 0, 1, 0 and 1, 1. Now you are told to rotate the triangle by 90 degrees at anti-clockwise direction and find out the new coordinates. To do this, at first, like the problem we have solved some time before, which involved a line, first define the rotation matrix. And your rotation matrix will go like cos theta. That means in this case, theta is 90 degrees, then minus sine theta, minus sine 90 degrees, then you have 0, then you have sine 90 degrees, cos 90 degrees, 0, lastly you have 0, 0 and 1. Okay, now you have to solve the problem for all the three vertices. That means for A, then you have to solve it for B, then you have to solve it for C. So for A, x old is 0, y old is 0. So to find the new coordinates after rotation, you need to multiply the input vertex with the rotation matrix tr multiplied with x old, y old, 1. Yes, done. So if you do this multiplication, you will get the new coordinate for this point A after rotation. Now you have to follow the same course of action for the remaining 2 points, that is point B and point C. What will change? X old and Y old will change here and here. Try to solve this yourselves and come up with the solutions. And this was, uh, I believe, all about rotation in 2 dimensions. Next, we will look about scaling. So, what actually scaling is? In computer graphics, scaling is a process of modifying or altering the size of the objects. So, to get an idea of scaling as a whole, first look into this diagram. Uh, I think I have to zoom, I have to shrink this a little. No, need to expand this a little more. Uh, yes, drag it a little to the middle of the screen. Now I think it is now visible to all of you. Here you have a polygon ABCD in a XY coordinate system. You can see it here. Now, after scaling, that means you have magnified it. After scaling, you get an enlarged version of this, right? So, what are the properties of scaling? Scaling may be used to increase or reduce the size of object. You can see into the example that the size of the object, in this case, the polygon ABCD, have been increased. Um, Scaling subjects the coordinate points of the original object to change. In other terms, have a look into the first diagram which we have before scaling. What are the coordinate points before transformation, before scaling? Can you figure it out? Okay, let me ask you, what is the coordinate of point A? Give it a thought, write down the answer into the chat box. I hope you have been able to figure it out. It's very simple. If you have a look, you can find that the coordinate for point A is 0 and 3. Now, after the scaling operation has been performed, the new coordinate for A is 0 and 9. So you can say that this OA line, DA line, has been enlarged. Uh, Before scaling, its length was uh, 3 blocks. Now, after scaling, its size is equal to 9 blocks. So the second line is justified. Scaling subjects the coordinate points of the original object to change. Now, scaling factor. Scaling factor determines whether the object size is to be increased or reduced. How it goes like is, say this is OA dash. Now you can see that from this example, OA dash equals to 3 multiplied with OA, or in other terms, you have increased the size of OA 3 times. So this is basically your scaling factor. Now, scaling factor determines whether the object size is to be increased or reduced. If scaling factor is greater than 1, then the object size is increased. In our example, you can see that scaling factor is 3. That means the scaling factor is greater than 1. So, the object size has been increased. Now, can you say what would have happened if the scaling factor is, say, 0.5? Give it a thought and write down the answer into the chat box. If the scaling factor in our example is 0.5, will the length of line OA be increased or decreased? Write down the answer into the chat box. Give it a thought. I hope You have got some idea until now. From this multiplication itself, you can say that the length of the line will be reduced to half if you multiply the original length with something less than 1. So if scaling factor is less than 1, then the object size is reduced actually. So these were some of the properties of scaling in two dimensions. Now let we try to derive the mathematical formulation for this scaling thing. So here the problem goes like you have a point object O whose initial coordinate is x old, y old. That means in your 2D space you have a point O somewhere whose coordinate is x old and y old. Now let me move towards generalization. Rather than moving the factors in numerical terms, we represent them with some variables. Scaling factor for x-axis is Sx and scaling factor for y-axis is Sy. You can see that scaling factor along two different primary axes can be different, and this thing is evident from this diagram also. Here you can see that uh, along the y direction, the original polygon has been increased 3 times. So the scaling factor along the y direction is 3, but along the x direction, it has been increased twice only. So along the x-axis, your scaling factor is 2 in this particular example. Now, if you generalize the scaling factor for x-axis let is Sx and say scaling factor for y-axis equals to Sy. New coordinate of the object O after scaling is x new, y new. So once you have scaled it, then obviously we'll get a new coordinate and say this new coordinate is x new and y new. So what is going to be the mathematical formulation for this x new and y new in terms of x old and Sx, y old and Sy? You are basically multiplying x old with Sx to get x new and y old with Sy to get y new. If you have followed this discussion here, I think this is clear to you. Now, if you express these two equations in a single equation involving matrix, this can be the matrix representation of a scaling matrix in Cartesian coordinate system. Now, let me try been able to put some sense in your minds. Now, to put those ideas into work, let me try to solve a real-time problem. And the problem goes like, given a square object with coordinate points A equals to 0, 3 and the coordinate of B is 3, 3, C 3, 0 and D 0, 0. Apply the scaling parameter 2 towards x-axis and 3 towards y-axis and obtain the new coordinates of the object. So now I will like you to give this problem a little thought for a while and try to come up with the solution procedure. In the meantime, I will copy the problem into a whiteboard so that we can discuss it. Last page, extra page. I will paste the text here. Yes. So I hope you have been able to come up with some solution procedure. Just have a look at the problem once again. You have a square object in a two-dimensional place, and the two-dimensional space is defined by xy system. So the coordinates for the vertices of the square objects are a, 0, 3. That means somewhere here is your a, and its coordinate is 0, 3. Then you have a coordinate b, 3, 3, somewhere here. Then you have c at 3, 0. It will be somewhere here. It is c and its coordinate is, sorry, I have done one mistake, I believe. So I must plot the points once again. Please be with me. A is 0, 3. So it will be here. 0, 3, and it is your A. Then you have your B. It is at 3, 3. Then you have C, which is at 3, 0. 3, 0 point should lie onto the x-axis. So here is your 3, 0 point plotted onto our xy two-dimensional Cartesian coordinate system. And lastly, you have point D, which is at the origin. D, which is at the origin. So its coordinate is eventually 0, 0. So this is our square, and our square looks something like this. It's not. Yes. Now, as the next line, you are being told to apply the scaling parameter 2 towards x-axis and 3 towards y-axis and obtain the new coordinates of the object. I hope until now you have been able to figure out how we will solve it. At least you have noticed how to apply transformation matrices while we were discussing the rotation thing. So here scaling. Now scaling, so TS is our scaling matrix, and if you have followed our generalized discussion about formulation of scaling matrix, you can recall that at the first point, that means at the first location of the matrix, we had Sx. That means scaling factor along the x-axis. Now into this problem, scaling factor along x-axis is 2. So you should write 2 here. Then at place of y, what you had? You had 1, 0, then 1, then you have Sy here, and Sy indicates the scaling factor along the y-axis, and in this problem it is 3. So write 3 here, then 0, and the last row for homogeneous coordinate introduction, and here goes our scaling matrix. Now what you have to do, you have to multiply each and every point with this scaling matrix to arrive at the locations after scaling. That means, say for point A, we want to solve this problem for A, and for point A, x old is 0 and y old is 3. Now, to find the after scaling point, you need to multiply this scaling matrix with the input points. That means x new, y new, and one vector equals to ts multiply dot product or multiplication with x old, y old, 1. Once you sorry, this is y old. Once you solve this multiplication, you will get the new point after scaling this point D by an amount 2 towards x-axis and by an amount 3 towards y-axis. Now you have to do or repeat the same operation for the remaining 3 points, that is point B, C, and point D, and end result is your coordinates for the square after scale. So this was all about scaling. Now uh, come to the next uh, transformation, which is reflection. Reflection can be performed in two ways. It can be done with respect to x-axis, and it can be performed with respect to y-axis. So if you do the what I say reflection with respect to x-axis, you are getting the reflected object somewhere here. In this diagram, the triangle ABC has been reflected with respect to the x-axis. Now, can you please tell me, if you reflect this ABC triangle with respect to the y-axis, in which quadrant your reflected object will be in? Write down the answer into the chat box. I hope you have been able to come up with some solution. If you reflect this ABC triangle with respect to y-axis, your resultant reflected triangle will be into the second quadrant. So let me look into the salient features of this reflection thing. Here are some of the properties of reflection. Reflection is a kind of rotation where the angle of rotation is 180 degrees. Um I hope it makes some sense to you. If it doesn't, just observe this discussion. Say you have a point object x here. Now, if you reflect this x point object with respect to y-axis, the new point, reflected point, will be somewhere here, x dash. Now say, in spite of reflection, you do a rotation by an angle of 180 degrees in anticlockwise direction. What will be the result? So try to figure it out. I hope you have been able to sort it out. Uh, then come to the next point. The reflected object is always found on the other side of the mirror. It is actually mirror phenomena. The size of reflected object is same as the size of original object. Uh, uh, Now let me have some deeper dive onto this. You have a point object O which has to be reflected in a two-dimensional plane. Initial coordinates of the object O is x O, y O, and new coordinates of the reflected object O after reflection is x nu, y nu. So what will be the equations for this reflection? Now have a look at this diagram as it has been mentioned into the statement. You have a point x old, y old, then you need to reflect the object, and after reflection the coordinates are x nu, y nu. Now when we say reflection, we need to mention some other thing also, and that is with respect to which axis the reflection should be performed. It might be with respect to x-axis, it might be with respect to y-axis. Say, for the time being, at first we will reflect this point object xo, yo with respect to the x-axis. So clearly, after reflection, you will get the reflected object somewhere here. This is your x nu, y nu, right? So can you express x new and y new in terms of x old and y old? Give it a thought, pause for a while, and write down the answer in the chat box. Hope you have been able to some solution. Now have a look into the points. You can see that while you have reflected the point object with respect to x-axis, the x-coordinate has not changed, but y old has now become minus y old, right? So after reflection, the things goes like x new equals to x old as it was into the diagram, x new equals to x old, and y new equals to minus y old. Y new equals to minus y old. So from this, you can actually uh, derive the things. If you append a homogeneous one here, now have a look into the uh, matrices. So for our previous discussion, we have reflected the object with respect to the y-axis, where it has gone. Yes, no, not here. It must be somewhere here. No, it is not here. Yes, here is it. So if you represent this in matrix format, your x new and y new becomes 1, 0, 0, minus 1 multiplied with x and y old. You can see if you do the matrix multiplication here, you will arrive at this conclusion, right? And this representation or this matrix has been formed for Cartesian coordinate system. Now, if you want to formulate same thing for homogeneous coordinate system, you will have something like x new, y new, and 1 equals to 1, 0, 0, 0, 0, 1, 0, 0. Oh, I've done some mistake, I think. Yes, here it should be minus 1. 0, 0, 1 equals to x old, y old, and 1. If you do this multiplication, once again you will arrive at this conclusion. Now you will have your homogeneous one as the last line. Now this was the derivation for what I say uh, reflection Sorry, I must move it somewhere here. Reflection with respect to uh, x-axis. So that's all for today. I hope you have been able to learn something if you have observed everything carefully. Uh, One thing I would like to mention once again is that don't forget to write your name and university roll number into the chat box, and that is your attendance for this today's live session. If you have not done this yet, done it right now. As we are near to the end of the session, I'm going to disconnect now after a while. And as I always say, at first read the study material, then go through the video once again, take notes, keep a notebook and a pen with you always while you are watching this live sessions, as well as while you are watching this later on. Take notes. Then read the material once again carefully through in between the lines. Hope you have learned something. Have a good day. Stay safe at home. Goodbye.